Hello, this is Lab 2 by Zach Braun. The problem that we had to answer was to observe the motion of an object that is dropped from rest and falls somewhat slowly from a height. This is just slower than a rock. The process I'm going to go through is first we're going to do an introduction, then we're going to do a tracker video of my object, which was a paper ball, and a computer model with gravity only. Then we're going to discuss the fundamental principle that I applied there, and in the next computer model, which is of gravity and drag. And then I'm going to compare the two computer models, and I'm going to end the discussion with a conclusion. As you can see, we have a lot to go through, so we might as well get started with the tracker video. Here's the ball as a reference. This is my tracker video. The movement starts at 156 frames and ends at 173 frames. This is a total of 17 frames. My object falls for 0.708 seconds. As you can see here, the total distance is negative 2.57. My y direction, this is y negative, y positive, x positive, and x negative. Now that you've seen the gravity-only model, let's review the physics behind it. First, let's start with a fundamental principle. We start with delta P equals F net delta T. Delta P can be written as PF minus PI equals F net delta T. We then add the PI, and we get PF equals PI plus F net times delta T. Divide the whole thing by the mass, and we now get VF equals VI plus the quantity of F net divided by the mass times delta T. This is my gravity-only Python model. The first thing that you should notice is the initial conditions. It was 0.002504 kilograms, and the position of the ball was 0.013 because it wasn't exactly at the origin when I started. The next thing you should notice is the delta T is very small, 0.001. This is because it only took 7 seconds for it to fall. Here is my loop. Because there's only one force, which is the weight force, and weight equals negative ball.m times g times j hat. That's also equivalent to W equals negative mg j hat. Let's run the model now. As you can see that the graph decreases to the right and that my displacement is going down, of the weight force going down. Now that we've found our fundamental principle, let's draw out the motion that we observed in the Python video of gravity only. Now let's draw the force that was acting on the dot, which was our weight force, and weight equals negative mg j hat. Because weight was the only force, our body went downwards, following the force. Now in our next code, we depict gravity and drag. So let's take a look at what that free body diagram would look like. Now let's add in our weight force. And now the only difference is that we have a drag force that opposes it. Drag force is due to air resistance. As you can see, the drag force is a lot smaller. This is because it's turbulent drag. This drag can be even further divided into parasitic drag and lift-induced drag. Drag opposes the force of gravity, which is also known as the weight force. Since the drag force has a smaller arrow, this means that it uses less newtons to use its force. This means that the object still goes down. Let's now take a look at this model in action using Python. Everything is the same as the gravity-only Python model. The only difference is that I added in the force of drag. The force of drag is negative b times the magnitude of the velocity squared times j hat. Just like in our free body diagram, we sum the weight plus the force of drag to get the net force. The net force is then used to find the velocity and position update, just like in Lab 1. Let's now analyze all the data together, the data from the tracker, data from the gravity-only Python model, and the gravity and drag Python model. Here's a comparison of all my data models. The red is the gravity and drag, the blue is gravity only, and the green is the tracker data. As you can see from the data is very closely resembled. The discrepancies between the tracker and the gravity only is caused mainly due to drag, and the discrepancies between the tracker and the gravity and drag is caused by those air pockets that were in the paper ball itself, pushing it up. You can also see that the velocity of the red gravity and drag is a lot steeper than the gravity only. You can find the velocity through analyzing the slope, but you can see just here that the red one is just a steeper graph than the blue one, which is gravity only. You can also see how tracker has a shallower slope, which is a smaller velocity at the beginning, and then towards the end it has a steeper slope. I believe this is due to, once again, the air pockets at the top pushing it up more than they did at the bottom. Now that we have analyzed the graphs, let's look at an important concept called terminal velocity. The velocity of a falling object is the velocity of the object when the sum of the drag force F sub d equals the force of gravity F sub g. F sub g is also known as the weight force. As you can see here, terminal velocity occurs when W equals F sub d. Did terminal velocity occur in this lab? Or could it be predicted by the models that we created? Well, I think that the gravity-only model has no terminal velocity because there's no force to oppose it, so the acceleration is always going to be increasing. Gravity and drag is a good model because eventually the drag force will grow a big enough arrow or enough newtons of force to oppose gravity so that F net will equal 0. I also think that the tracker is a good model. It's possible that we could see terminal velocity eventually, but we need more data points to tell. What if the object was given an initial velocity? I'm going to find out what happens if the object has an initial velocity using the Python computer model. Let's look at that now. The only difference here between my original Python models is that I have an initial velocity of -10. As you can see by the two arrows, the drag force equals the weight force a lot sooner. You can also see that by the graph how it is a much smoother line because the velocity is no longer increasing, which is also called the acceleration. The graph slope is a lot smoother. This means that the velocity and acceleration peak were reached at a much sooner time. In conclusion, I'd like to leave you with the following points. Thank you for watching.